Hey everyone. Today you can see on the screen we're going to walk through a number of examples on solving systems by a method called elimination. And so this is going to take us a different approach maybe than how you've solved systems in the past. And so I want to jump right in with us using this process called elimination. Okay, here we go. So what you see on the screen right away, there is a system of equations, and I'm hoping that you're coming to this video with understanding what a system is, the fact that we have multiple equations. So I'm going to take the approach that we understand how to solve a system by using substitution. And that today, where it changes is we're just going to learn a new method, or maybe fine-tune a new method. So if we were walking through and using substitution, we would be calling that equation 1 and that equation 2, and probably taking equation 2 and isolating 4x. Then you could sub 2 back into equation 1 and so on and so on. When we go through that process of subbing 2 back into 1, it's important for us to know that really all we're doing now is we are getting an equation with one variable. And what you see in that last orange line, you now have an equation with one variable. You have the means to solve that. So for us to solve a system, it's important we have to get down to an equation with one variable. So if I was to twist that wording a little bit, really then what we need to do if we have equations with two variables is we need to eliminate a variable. And that's really what we did when we used substitution. We subbed into another equation to get it to one variable, therefore eliminating a variable. Well, elimination is a little more of a direct way to get there. So what I'm going to do is I'm going to erase everything that we just wrote down with the exception of calling those equation 1 and 2. That's universal. Now, my theory behind, or the theory behind, using elimination can get a little confusing, but if you hang tight, I think we're there. What you have in equation 1 is a statement that is true. Why is it true? It's because you've been told it's true. You've been given an equation that says 4x plus 2y equals 15. And so what you have then in equation 1 is a relationship between x and y, where when we multiply x by 4, multiply y by 2, and add them together, we always get 15. You've been given that. It is a statement that is true. You've also been given another statement that is true in equation 2. And since you have two true statements, then that means that you can manipulate those true statements however you wish. And as long as we don't do something mathematically incorrect, then the outcome between those two true statements will also always be true. And so what we can start to do is we can do operations between those two equations. As long as I add those two equations together, and I do it correctly, then my outcome is true. But I don't have to add them. I could subtract them. I could multiply them. I could divide them. Any operation I do between those two equations, as long as I do it correctly, then my outcome is also true. And that's the theory behind elimination. So if I was to take a look at those two equations, and my goal was to eliminate a variable, well, I'm going to just take like this, okay, I'm going to just stumble my way through approach. And how about I try taking equation 1 and adding it to equation 2? Now, I'm just going to put a little total line down here, just so we can see it. But I'm going to add those two equations together. So let's look on the left side of my equal sign. I'm going to take my 4x and I'm going to add it to my 1x. That's going to give me a 5x. I'm then going to add a positive 2y plus another 2y. That is going to give me a positive 4y. And then on the right side, I'm going to have a 15 added to 1. There is a 16. What I just built in gold there is a true statement, that 5x plus 4y must equal 16. The problem was it didn't really help me. Because notice, all I did was just build a third equation that has those same two variables. If my goal is to solve the system, then I don't want two variables. I want to eliminate one. So you can just see that by adding those two equations together, it did not help me. So let me get rid of that gold. And let's stumble instead and say, well, why don't I try to subtract them? Okay, just for some visual, I'm going to put down this total line just so we can keep everything clear. Now, let's subtract our two equations. Okay, 4x subtract an x is a 3x. Now, a 2y subtract a 2y, well, I could write this down, but I hope that we don't. If I have something and I subtract itself, then those are going to cancel out. And when they cancel out, that leaves me with 0. Hey, look at what just happened. On the left side of my equal sign, my y terms just canceled out. They eliminated. Beautiful. I actually really like that. And now, when I subtract my 15 and my 1, I get 14. Look at what I have in my equation. I have an equation with one variable, and it's actually a really simple equation to solve. What I just did was use the process of elimination. And that enabled me to create an equation in one variable. And I can solve that. So for me to now isolate for my x, I need to divide out my 3, and there we go. A much more direct approach to getting down to being able to solve an equation in one variable. Now, what you'll also notice is we're not done solving our system, so let's be clear on that. But it was a more straightforward approach to being able to find the value of the first variable. Take a look at my blue on the screen and you will see my communication. There is how I write down that I subtracted the two equations and I subtracted them in that order. Okay, well, we're about halfway there maybe. But what you're going to find is the rest of your system should pretty much be automatic. If we've worked through solving systems by substitution, our next action should be automatic, that we are going to sub x equals 14 thirds back into one of our original equations. And I'm hoping that we're going to sub it back into 2 because 2 seems to have smaller numbers. So I'm just going to wrap around up here. In equation 2 now, my x is 14 thirds. And I can now go through and solve. I can get rid of my 14 thirds, which means I need to subtract 14 thirds. That means I need a common denominator. So 1 is going to be 3 thirds, subtract 14 thirds. That is going to give me a negative 11 thirds. And when I divide out my 2, I'm going to multiply that bottom by it. And the only thing left for me to do now is state my solution. That I have an x value of 14 thirds and a y value of negative 11 sixths. And there we go. There is the act of us solving a system using elimination. Look, we even got some uglier numbers out of it with some fraction solutions. Okay, what I want to do for the rest of this video is to work our way through different scenarios using elimination. Okay, here we go. Okay, so let's take a look at the system I've given you in B. Okay, What's automatic? We need to talk about that system correctly. There is equation 1 and equation 2. Now, we are not going to rearrange those equations as if we were using substitution, but just a quick note on that substitution. If you take a look at both of those equations, you're either going to have to divide by 5 or divide by 3, divide by 4 or divide by 3. You're going to get fractions in a lot of cases. And probably for a lot of us, when we then solve our system using substitution, those fractions are going to slow us down, at the very least slow us down. So here is a big benefit to us of using elimination. Instead of trying to rearrange the equation, let's look at our two equations and try to figure out an operation we could do between both of those equations that could eliminate a variable. Well, if we took a look at adding or subtracting the two equations and we focused on our m terms, you'll notice if I add those two together, then I'm going to get 9m's. And if I subtract the two of them, then I'm going to get 1m. I would not have eliminated my variables. So I do not want to try to deal with my m's right now. But if I took a look at my m terms, there's my n terms. If I was to go through and add those two equations together, then I get 0. A 3n plus a negative 3n gives me 0. And that's what I'm looking for. I'm looking for terms that can cancel out. So I just found my way that I am going to eliminate my variable. I am going to take equation 1 and I'm going to add it to equation 2. Okay, I'll just put a total line down as a visual. And now I can do what it says in blue. I'm going to add those two equations together. So when I add my m terms together, I get 9. I add my n's together, they cancel out and give me 0, which is great. I add my constants together on the other side, and I just eliminated a variable. Beautiful. Look at my equation I have in gold. It is just in one variable. I can solve that nice and quick, and I even get something nice and neat like an integer. Okay, the rest is automatic. I can now sub my m value back into one of my originals. And I'll be honest with you, I don't know if there's much difference between those two. I might sub it in to equation 2 only because the numbers are a little smaller. So I'm going to get 4 times 3, which is a 12, minus my 3n. I can now isolate my variable, and I divide out, and there's my 4/3. Nice. Okay, finish off by stating my solution. And remember, we always state in alphabetical order. And I assume that you would be fine if you wanted to check that solution to take both of those values, sub them back into your equations, and see that we get the same thing. Okay, I want to take a moment for a second and just talk about maybe a little bit of a hint, a clue, look for, that's going to help you to skip over some of that, maybe guess and check of what operation do I do, so you can go directly to whether you should be adding or subtracting your two equations. Take a look at the system I gave you in B. We should be good to recognize that we have the 3's out in front of both ends. Really what we want is we want the same number. So when I box in those two 3n terms, that's going to be the term, the variable, that we can eliminate because they have the same coefficient. My decider then becomes, okay, well, should I add them together or subtract them in order to eliminate? And something that can really help you out. Look at the signs on the two terms. If I have one term that's a positive and one term that's a negative, I have opposite integers. And if I want to get those opposite integers to cancel out to give me a 0, then I need to add them together. So a positive value added to its opposite, the negative value, will cancel out and give me 0. So some way that people tend to think about it is if I have the different signs, then I know I'm going to add. Okay, I want to hop back and take a look at our solution from problem A. Okay, what you see on the screen right now is our solution from problem A. Now, if I zero in on the terms that have the same coefficient, this is going to tell me I can eliminate my y's right now by adding or subtracting. Both of them are the same sign. So I have a positive of something and another positive something, and I need them to cancel out. Well, the way that I can get them to cancel out is to subtract them. If I have two of the same thing, then the way I get them to get 0 is to subtract them. And you can see that that is your shortcut to subtracting between. So one quick way that people tend to look at it: if I have different signs, I know I'm adding. If I have the same sign, I know I'm subtracting. Okay, let's jump in and play around with another problem. Okay, you see the system looking in problem C. You have your first equation, 2x plus 5y equals 8. You have your second equation, 2x minus 3y equals 17. To solve the system by elimination, we're first looking for the same coefficients, and you see that. There's your 2's. And so we can go through then and we can eliminate our x's. If you use what we just talked about, you'll notice that we have the same sign on both of those terms. And so for me to eliminate two of the same thing, then I need to take them and subtract. So I'm going to subtract equation 1 and 2, and I'm going to do it in that order. I'm going to take equation 1 and then subtract equation 2. Again, some people like the total line just as a visual. Okay, now I'm going to go through and I'm going to subtract each of those equations. 2x subtract 2x, those cancel out, which is great. I now have a 5y subtract a negative 3y, and there is your common mistake. Be very careful. I am correct in me writing down 8y, but I would have bet that we would have had a bunch of people that would have written down 2y. Over and off to the side, I'm just going to write down what we just did. We are taking our 5y and we are subtracting a negative 3y. Remember, I'm subtracting my two equations from each other. And when I write that out in orange, you can see that I'm subtracting a negative, which means I'm really making it more positive. Easily, that's going to be your number one trap. So just be careful. Okay, I can now take my 8 and subtract my 17. There is a negative 9. And now I have a nice easy equation. I've eliminated, and there we go. So what I would like you to do now is I want you to finish off this system on your own, and we'll just make sure that we can drill in the second half of our solution. So I want you to pause the video now. Okay, so we're back. So now I can sub in my y equals negative 9/8, and I'm going back into one of my originals. I don't really see either of those equations as being significantly easier than the other. I think I might just go back into one only because of the 8 on the right side rather than the 17. So in order to do that, I've got my 2x plus my 5, sub in my y value, and now I have my equation with just x's. Okay, I can simplify all my terms. Then I can isolate my variable term, so I have to get rid of that negative 45/8. That means I'm going to need my common denominator. So 8 becomes 64/8. I can simplify my right side, and that gets me 109. And now when I divide out my 2, there we go. I take a look at my denominator. That's only made of 2s, so I know that that is fully reduced. And I need to remember to write my solution. Alphabetical order. And that got a little sloppy. My x value first. And my y value second with some nice ugly fractions. There we go. So I would argue to you, if we can take a look and work our way through that system, then you should be pretty confident in using elimination. Okay, the rest of our examples for today are just looking at some things. What happens if we can't eliminate something so nice and neat? Okay, let's take a look at another one. Here we go. So I want you to take a look at the system that I gave you in D. Clearly, we have equation 1 and we have equation 2. And now we're going to look to eliminate a variable. However, you may notice, right now you cannot eliminate your x's because they do not have the same coefficient. But you can also notice you cannot eliminate your y's because they don't have the same coefficient. So, up until this point, maybe elimination only seemed to you to be a viable solution or method for solution when you had the same coefficient on a variable. Well, that doesn't mean then that all of a sudden, okay, well, we can't use elimination. It just means our actions maybe have to be a little different to get us to our goal. That when we take a look at those two equations, we wish that we had a variable with the same coefficient. So our argument is going to be, well then, why don't we just make it have the same coefficient? If I take a look at equation 1, I could have my x's, a 2, turn into a 3. Because I could take a 2, and if I multiply it by 3 halves, then that gives me 3. Except, I don't think we want to be multiplying stuff by fractions and making things ugly. So, I take a look at my two equations, and I notice that if I focus in on my y's, I could make my y's have the same coefficient. If I changed equation 1 and I doubled everything. Okay, I want to have a quick discussion on that. Notice what I'm going to do is I'm going to take equation 1 and I'm going to multiply it by 2. And we should be good that as long as I do the same operation to both sides of my equation, then my equation stays in balance. So if I took equation 1 and I doubled all parts of the left side, so I doubled the entire left side, then as long as I double the right side, that equation is still true. So you take a look at that orange equation I just wrote, and then take a look back up at equation 1, and you'll notice they are the same equations, just unsimplified. Look at my orange equation again and notice that we have a common factor of 2 in each one of those equations. We could divide it out, and if we did, we get back to equation 1. You'll also notice we cured our problem for elimination. Now look at both of my y terms, and we'll see, hey, I got the same coefficient. I can now eliminate my variable. Okay, we've got some formatting. You just unsimplified an equation. That means it gets a new equation number, and man, is that a sloppy 3. So that now becomes equation 3. It's important for us to note, equation 1 and equation 3 are the same equations. But because I've unsimplified it, it gets a new equation number. And so now what I'm focusing in on, since equation 1 and equation 3 are the same equations, I'm really focusing in on this like new system. the system between equation 2 and equation 3. And now I can look at those and I can eliminate my variable. So what I want you to do is focus in on that system we just talked about, equation 2 and 3, and see if you can finish off solving that system using elimination. Okay, pause the video now. Give it a go. Okay, we're back. Now, for me to go through and solve that system, I am I don't know if I want to say believer in, but I prefer to always have positive coefficients on my variables. So I want to walk through something that can happen. If I put my little total line down again, I may choose to take equation 2 and subtract equation 3 because I see they both have the same sign on my y's. But when I do that, I'm going to get negative x equals 0, and I might not like that negative. So my focus always becomes, I really want to have a positive leading term, a positive coefficient on my variable. And so my action in this case would actually be to take equation 3 and subtract equation 2. It might seem small right now, but it's going to save me some time or some effort or some focus later on. Okay, what does that give me? Well then, my 4x subtract my 3x is an x. My 2y subtract 2y cancels out. My 6 subtract 6, there's my 0. And look, I just actually solved for what my variable is. X equals 0. Okay, I can now take that x equals 0 and I can sub it back into one of my originals. And you notice I keep saying one of my originals. I could sub it back into my orange equation because 3 is equation 1. Except, and this is an important thing for us to consider, that orange equation was manipulated, and you did the manipulation. Is it possible that you made an error when you came up with that orange equation? Absolutely yes, we are human. Therefore, my orange equation could be wrong. That means when I just solve for x equals 0, that could be wrong. And if I now took that incorrect value and I subbed it back into equation 3, I'm going to take something that's wrong and sub it back into something that's wrong. I'm going to be more wrong. I'm going to be farther away from my correct solution. And so a piece of advice I'd like to give you, sub it back into one of your originals. They were given to you. You know that they are true. So when I'm considering what equation to sub it back into, I'm considering equation 1 or 2. And in this case, equation 1, and I got to get rid of that, would be the easier of the two equations just because I have a y and not a 2y. So I'm going to sub it back into 1. 2 times 0 is 0, and that gives me a very clean equation of y equals 3. I actually have my full solution now. So I just need to remember, state my final solution, x coordinate, y coordinate, and we are good. So the takeaway from the system that we've dealt with in D is we may need to manipulate an equation first in order to get the same coefficient to be able to use elimination. Focus up on my blue on equation 1. We had to manipulate equation 1 by doubling it in order to ensure that we had the same coefficient on both variables. I think you'll still notice that still makes it pretty efficient for us to use elimination compared to, let's say, substitution. Okay, let's keep playing around with some systems like this. Here's another. Okay, let's take a look at E. You can see the system I've given you in E. Everybody should be good to label that as equation 1 and equation 2. You notice you do not have the same coefficient on your x's nor your y's, and therefore we need to figure out how we're going to manipulate those equations. So I want to give you a chance to just take a moment, try it on your own, and we'll see if we match up. So I want you to try to manipulate one of your equations to get the same coefficient in front of both your variables. Okay, pause the video now. Okay, we're back. I am really hoping that I had everybody choose to multiply equation 2 by 5. Because you would see you could multiply by an integer, and when you do that, you're going to get 5s in front of both your y's. So we can now go ahead and we can multiply everything in equation 2 by 5. We now just unsimplified equation 2, so it gets a new equation number as equation 3. And the system we are now working with is equation 1 and equation 3. Okay, I think you should be good to be able to finish off solving the system now. Let's use this as a bit of a gauge to try it on our own. I want you to pause it now and finish it off. Okay, pause it now. Okay, we're back. So we take a look at those, and it doesn't matter what order I add in. So I am going to add equation 1 and equation 3 because I notice that I have different signs on my y terms. Okay, I'll put in a little total line. And now when I add my x's, I'm going to get 17x. I add my y's, they cancel out. I add my constants on the other side. I'm going to divide that out. And actually, if I take 68 and I divide it by 17, that's going to give me 4. Nice. So I can now go through and I can sub x equals 4 back into one of my originals. And I think the easiest one to sub that back into right now is going to be equation 2 because I have a coefficient of 1 on my y. So I can replace my x with 2. There is a 12 minus y equals 12. Well, pretty quickly, when I get my 12 minus 12, I'm going to get a y value of 0. And therefore, I have my final solution. There is an x value of 4 and a y value of 0. Nice. Okay, hopefully we matched up and you were feeling much more confident in using elimination to go through and solve. Okay, here comes another one. Okay, you can see the system that I've given you in F, and there is equation 1 and equation 2. And now we take a look and we're like, oh no. For me to change a 2 into a 5, I'm going to have to multiply by a fraction or a decimal. For me to change a 4 into a 3 or a 3 into a 4, I'm going to have to do the same. And so now we may be thinking, oh, so now I've got to introduce some fractions that I'm going to multiply by. My numbers are going to get ugly. You know what? This is no better than substitution. I want to make sure that we have a good idea in our head. If we can manipulate one equation, then we can manipulate 2. And so we don't have to use fractions in order to use elimination. It just means we're going to multiply both equations by a value. Now, I'm going to do this kind of in 2 different ways because I just want us to see something really quickly. And I don't think that either one way is better than the other. I could take equation 1, and if my focus was on the x's, getting the same number in front of my x's, then one of the easy things I could do is multiply equation 1 by 5 and equation 2 by 2. And notice, in both of those cases, my equations would both have 10 x's. The same number of x's, and now I could eliminate my x's. But I could have also multiplied equation 1 by 4 and equation 2 by 3, and that would have given me 12 y's, and therefore the same number of y's in both equations, and I could have eliminated my y's. That when I'm taking a look in this system, either of those methods, either of those decisions would have basically got me to the same thing. And that's why I would argue, I don't think that there's one way that's better than the other. Multiplying by 5 versus multiplying by 2. Multiplying by 3 versus multiplying by 4. Those are all going to keep my numbers relatively the same. They're not blowing numbers up and making them huge. So what I want you to do is take one of those actions. Multiply equation 1 and 2 to eliminate your x's, or multiply equation 1 and 2 to eliminate your y's. And let's see if we match up in the end. Okay, pause the video now, give it a shot. Okay, I'm going to work my way through. Just because, let's say, 5 is a bigger number, I'm going to choose to multiply and get rid of my y's. So I'm going to multiply equation 1 by 4 and equation 2 by 3. It makes no difference. If I do that, I'm going to create 2 new equations. If I focus in on multiplying equation 1 by 4, then that is going to give me an 8x plus 12y is equal to 20. I just unsimplified that equation. That now becomes equation 3. Well, in order to get the same number of y's, I'm now going to multiply equation 2 by 3. That gets me 15x plus 12y equals 48. I unsimplified equation 2, so that needs a new equation number. There's my equation 4. Okay, I now have 4 equations, but I am focusing in on my manipulated versions, 3 and 4, to now solve my system. I did that to make my decision to eliminate my y's, and since I like having positive coefficients, I'm going to take equation 4 and subtract equation 3. That then, when I go through and I subtract them, that's going to give me a 7x equals a 28. Oh, and I love getting numbers like that because now I get an integer again. Nice. Notice here's an instance where had I taken equation 3 and subtracted equation 4, I would have had negative 7x equals negative 20, and it just would have introduced negatives, and now I was able to avoid that. Okay, I'm going to wrap my solution around because now I need to sub equation 4, x equals 4, back into, and as I stated previously, go back into one of your originals because you know those things are true. So I'm going to sub it back into equation 1 because equation 1 just has smaller numbers. When I do that, I'm going to get 8 plus 3y equals 5. So 3y equals negative 3 and y equals negative 1. State my final solution, my x value and my y value, and you now just solved a system that required manipulating both equations to use elimination. Take a look back at your original system. Imagine rearranging those equations to isolate one of your variables. You're going to get fractions. It's going to slow you down. You may make some mistakes. I think even with having to manipulate both equations, to multiply both of them, you're still faster using elimination than what you would have been using substitution. So I'm telling you, when you have a linear system, you want to make your default method of solving elimination. Don't be a substitution junkie and always use substitution. But when you have a linear system, those two equations, both of the same degree, you want to make elimination your default method. Okay, let's play around with a couple more. We'll see how well we're doing with elimination. Okay, I want you to take a look at the system I gave you in G. And yes, that system became a lot uglier when I gave it to you. But we're not going to really take our time going through G. I just want to point out to you a couple things in using elimination. Well, you should notice that you have a system of equations right now that are unsimplified. Notice, take a look at equation 1. If you expanded all those brackets, you would have the ability to collect some like terms. Same thing in equation 2. So really all that was given to you was an unsimplified system. That should not affect how you go through to solve. I just want to point out a couple things. First off, I am going to simplify both of those equations first. So I'm going to start maybe with equation 1, and I can expand my brackets. And really, we hope that with that process, you can pretty quickly get down to a simplified version of equation 1. And you can do it where it's like perfect every time. Like almost, like yes, you can make a human error mistake in there, but I'm really hoping that expanding some brackets and collecting like terms, we don't make mistakes with that anymore. And so that equation that we just came up with, 4x minus y equals 9, that can be an automatic, like you expect that to be perfect, the best version of equation 1. So I'm hoping then that we could do the same thing with equation 2. And you could go through, and I'm going to go quickly and expand in. We could clean up what we have on both sides. We get to this part where now, because we have a negative in every term, I may take a moment to just say, hey, I'm going to divide both sides of my equation by -1, and I'm going to clean up that equation just so I don't have to deal with so many negatives. But same thing as I stated earlier, you're so good at going through and expanding brackets and collecting like terms that you have such confidence that that new version of equation 2 is perfect. Okay, I want you to focus in on those two versions of equation 1 and 2. Because those are going to be the versions that you're going to use elimination on. And I'm not going to go through and solve this system using elimination. I hope we could see probably the best action for us would be to take equation 1 and multiply it by 2, because then you could add together your two equations and eliminate your y's. What I want to talk to you about with this system is, once you've solved for x, okay, so we multiply equation 1 by 2, we get a new equation 3, we then take equation 2 and equation 3 and we add them together, we eliminate our y's, so we solve for x. You now have this decision, and I'm just making up a number here, x equals 5. It's not x equals 5, but let's just say it's x equals 5. Now I've told you, take your x equals 5 and sub it back into one of your originals. This is a case where we have to kind of weigh, okay, how confident are we that we haven't made mistakes versus the ease of our work? And here's one where I would argue to you, you should be so confident in everything you did in gold on the screen that you shouldn't have to sub it back into one of the originals, because then you're going to have more work to do. That you should be good to sub it back into one of the orange versions of those, the gold versions, I should say, because you are so confident that you haven't made any mistakes there. And subbing it back into one of those versions will make your life easier. So keep that in mind when you end up getting a system of equations where those equations are not simplified. Okay, just something to consider as you move forward. Okay, now I want to throw a doozy at you. Okay, you take a look at the system that I've given you and things changed. So I'm expecting that at this point, you are really, really solid with being able to solve a system of equations with two equations. And now I just went and I threw a third at you. I want to take you through a process to be able to solve a system of equations with 3 equations and 3 unknowns. So you notice each one of those equations has an A, B, and C variable. That means for us to solve this system, We have to solve for all of A, B, and C. Okay, I want us to see that this is no different. It's really not in solving a system with 2. I now have to make sure that I label my equations, equation 1, equation 2, and now equation 3. Now, what's my roadmap for being able to go through and solve that system? Well, if I'm automatic at being able to solve a system with 2 equations and 2 unknowns, then that's really what I want to create. So I'm going to just draw something off on the side. This would not be a part of my solution. But if I could take one of the equations that I have here, and I could use it to eliminate the same variable in the other 2 equations. So, for instance, let's just say that I used equation 1 to eliminate my C. Then if I paired that up with equation 2, by adding or subtracting them, that's going to leave me with an equation with an A and a B in it. Remember, I'm just using that we're going to eliminate our C's. Well, if I now took equation 1 again, but I used it with equation 3 to eliminate my C's, then that would leave me with another equation with just A's and B's. And notice, we should be really good when we have 2 equations with just A's and B's. So you could finish off by solving that system. You would now know what A was, you would know what B was, and you could sub that back into one of the originals to figure out your C. And that's exactly what we're going to do. So I'm going to erase all of that roadmap, and now we're going to work our way through. This is a real opportunity for you to challenge yourself with some problem solving. If you have never solved a system of 3 equations and 3 unknowns, then I want you to try to pause the video, especially after our little roadmap, and see if you can tackle it on your own. Okay, but we're going to go through and we're going to solve this system. So try it on your own. Pause the video now. Okay, we're back. So if I am trying to link together equation 1, and equation 2 to, let's just say, eliminate our C's. Because right now I can't eliminate my A's, I can't eliminate my B's, I can't eliminate my C's. It's going to require some manipulation. Then maybe I just pick C. C would be nice and easy. I could multiply by 2. Well, B's would actually be nice and easy too, because I could multiply by 3. So I have options here. Let's just say I'm going to eliminate my C's just because that's what was in the roadmap. Okay, for me to do that, I'm going to have to multiply equation 1 by 2. That is going to give me a new equation. That new equation will be 4a plus 6b minus 2c equals 26. I just unsimplified that equation. I now get equation 4. I did that so that equation 2 and now equation 4 would have the same coefficient on my C's. So now I could go through and take equation 3 and add it with equation 4 to eliminate my C term. I'm going to try to match up my colors. There's my green. And so a 7a plus a 5b, my C's eliminate, is going to give me -1. And I just created my green equation. Oh my goodness, that is now equation 5. Okay, now this is where some stuff gets ugly. I'm going to shrink down my system because I'm going to need some more room. Okay, I just used a combination of 1 and 2. That means I can't use that combination again. 1 and 2 was used up. So now what I'm going to do is I'm going to focus in on 1 and 3 to eliminate the same variable, eliminate our c. So what I now need to do is I need to take equation 1 and I need to multiply that by 3. That's going to build a new equation, and it's coming in right down below. So let's take equation 1 and multiply it by 3. That's going to get me a 6a plus a 9b minus 3c equals 39. Yikes. That is now equation 6. But if I focus in, I'm now going to take my two equations, 3 and 6, and I can use those to eliminate my c's. So what am I going to do? Well, my c's have different signs, so I'm going to take equation 3, and I am now going to add that with equation 6. Okay, man, I'm really running out of space here. So when I go and I do that, that is going to give me, and focus in on your equation numbers, a 6a plus an a, that's a 7a. I'm now going to take a 9b plus a 14b, which is a 13b. That is now equal to 39 plus a negative 8. There is a 31. Whew. Things are getting ugly. That is now equation 7. Okay. You don't have to do this, but for some of us, this solution might be getting really ugly. What I want you to focus in on are my two green equations. That was the system that we should be pretty automatic with in terms of going through and solving. Now, if things start to get really ugly and get lost in your own solution, please feel free to rewrite out any equations and put them in an order, a form that's going to make it easier for you. So some people would prefer to say, okay, I'm just going to rewrite out what equation 5 is, and I'm going to write out what equation 7 is. And if I do that over here by itself, then you can kind of get away from some of the clutter elsewhere on the page. Now, you don't have to do that, and I would probably argue for a lot of us, if we tend to make transferring errors, you're copying down something and I made a mistake. That should have been a negative. I wrote it as a positive, or vice versa. Then I would not do what we just did. But I think for some of us, that can really help. Okay, you take a look at the system we've got, and that's a nice, easy one to solve, because take a look at your A terms. They both have the same number of A's. And so when I take a look at those two equations right now, I could take, and I'm just going to slide over my screen, equation 7 and subtract equation 5 to eliminate my A's. Okay, here we go. If I take equation 7 and I subtract my 5, my A's are gone. I would then get 8b. 31 subtract negative 1 is a 32. And now I get a nice easy equation that I can solve for B. Okay, you've now found B, so we can sub B equals 4 back into one of my originals, and one of my originals in this case is one of my green equations. Well, I'm going to sub that back into 5 because equation 5 has the smaller numbers. Okay, that is going to give me 7a plus 20 equals negative 1. So 7a equals negative 21. Hey, that works out nice and neat too. Another integer. And you've now solved for both a and b. The only thing left for us to solve for, we need to find C. So I'm going to slide that over a little bit because we can now take two variables' values and we can sub in both an A value of -3 and a B value of 4 into one of my originals. And one of my originals now is going all the way back to the system that we were given, equations 1, 2, or 3. Well, if I take a quick peek at that, I think I would want to sub back into 3. And again, just because numbers seem smaller. Well, if I sub all of that stuff in, an A value of -3, a B value of 4, then I get my equation with just a C. And so I can clean that up pretty quickly. And we have solved our system. The only thing left to do, put it in alphabetical order. There's your A value, there is your B value, there is your C value, and we are done. So there was a doozy for us, a system with 3 equations and 3 unknowns. I'm hoping that what we just went through gives you a roadmap, and whenever you encounter a bigger system, more equations, more variables, that this can be a roadmap for you to be able to solve. It also was a great stumper for us for today. Okay, your job. Jump in, get some practice, and make solving by elimination as automatic as possible. Okay, good luck.